Okay, last time we took a look at the right triangle and got our foundation for what we're going to add to it this week. This week we are going to add the concepts of the complex numbers. The complex numbers being the numbering scheme where we lay out real and imaginary numbers on a set of coordinates, whether it's rectangular or the polar, as we'll use later. So we're going to look at how we put these together, how we handle these two sets of numbers that are laid out so that we can start building the skills that we need for AC circuits and dealing with components like a capacitor and an inductor, and how we treat the analysis when those two component types are added and we change the source from a direct current to an alternating current. So we'll learn to solve the problems, add, subtract, multiply, and divide. Divide will require some special rules, and take a look at graphing the complex numbers. So complex numbers are numbers that have a real part and an imaginary part or component. We're going to see how they build on the graphs and plot their values. When we have capacitance and inductance, in addition to resistance in AC circuits, we're dealing with two types of components that are vying for the energy. One type of component is the resistor, which is an energy user. The other is an energy storer. Circuit resistance converts energy to some other form, usually heat or light, like we've talked about before. Capacitance and inductance store and then release the energy. We like to think of it as trading the energy back and forth. Thus, there are two kinds of power dissipation that we can calculate. The real part due to circuit resistance and the imaginary part due to the capacitance or the inductance. That's our reactance portion. The numbers that represent these variables have both real and imaginary parts and are called complex numbers. So we need to start looking at what do they look like? What do they look like when we start seeing them on paper? What's the result if we find the square root of a negative number? So we need to build what is the essence of this imaginary number. We need to build an operator. And in doing this, we start with this square root of a negative number. And in taking the square root of this number, the answer cannot be positive or negative. It cannot be a 6 or a negative 6 because the square of either of those numbers does not give us back a negative 36. We just get 36. So we need to find a way to parse out that negative number, but keep it in the mix so that we can use it to do our calculations. So if we look at the solution for the square root of negative 36, let's take the negative number and separate it from the number that we're actually going to factor down when we do the square root. So that we have two components, the square root of 36 and the square root of negative 1. And what this leaves us is 6 times the square root of negative 1. And that square root of negative 1 becomes an important component in imaginary numbers. A number of this form then is called the imaginary number. Imaginary numbers are numbers that result from taking the square root of negative numbers. In math, we use the letter I to represent that, and it's not a capital I, it's a little I. And we're going to make it italic. So it's used to calculate. So we don't use that square root of negative 1. It's easier to use the I. So what we end up with when we factor it out, we end up with the negative square root of the negative 36 is 6 times I, where I is understood to be that -1. The unfortunate thing in electronics is we already have a character. We already have a variable that we use when we're dealing with current. We call it I. And in AC circuits, we use a little I, and in DC circuits, we will typically use a capital I, or a capital character. Therefore, then we need to use something else. Well, in electronics, the variable, or the letter that's used, the symbol is the J. So from now on, we will use J to represent a -1. And what we're going to see is whenever we invoke that J, that's square root of -1, that is immediately going to tell you that the value for that coordinate goes on the y-axis, and you're going to see that. We place the J in front of the number to make it easier to recognize in the presence of an imaginary number. So that J ends up being an operator that immediately tells us we've got an imaginary number. So if we take a look at that expression again, the square root of -36 separated out, now we have J6. We always put, in electronics, we always put the J in front of the number. Okay, so we know that it's immediately telling us it's on the y-axis and it's the square root of -1. We use the word imaginary, and it may seem kind of strange to you. Why imaginary? Well, we use the word imaginary simply as a means of separating it from the real numbers. The real numbers we're going to see are all the numbers that relate to a real resistance when we do our circuit analysis. So the imaginary numbers exist, and they're useful then for analyzing AC circuits. What we are going to start to see then is we're going to use something called a vector, and more preferably a phasor representation, for identifying what's going on. The X, Y Cartesian system is good, but the polar system more accurately describes what we're going to be talking about. A vector is a line from the origin of a rectangular coordinate system to some given point. In electronics, we call it the phasor. So the phasor is really a contraction here of phase vector that describes more than just the vector, because it's usually describing or calculating the phase relationships between voltages and currents by use of vectors and phasors. And using the vector representation gives us a better picture of what's going on than trying to pick off an instantaneous value off of a sinusoid. But you're going to see that they relate as you move through your studies in engineering technology. A phasor then can be specified as either rectangular or polar. Okay, so either one of those are working systems to help us use vectors and phasors. So if we look at a graphical representation here, let's say that we've got a vector that is creating a resultant or some value that is a real and imaginary number. And we can see that if it lies on the x-axis, that we just have 4, the real part, and 0 for the j part. If we rotate it 90 degrees, in the first 90-degree rotation, the real part goes to 0, but the imaginary part now becomes plus j4. If we rotate it another 90 degrees, we end up with just a real part in the negative direction and no imaginary part, that is 0. And if we rotate it another 90 degrees, we end up with no real part and an imaginary part of minus j4. And then we go back to just the real part. So this is a graphical representation of what the j is really doing with a simple example. So with our j operator, in mathematics. This is actually what mathematically we're going through. So if we defined j as the square root of minus 1, then j squared must be minus the square root of minus 1 times the square root of minus 1. Well, in multiplying those together, we lose two things, the square root. So you can see the j really is a number that we can handle mathematically. J cubed, then, minus square root of minus 1, square root of minus 1, square root of minus 1, or minus 1 times the square root of 1 gives us a negative j. And so you can start to see a pattern occurring here between odd and even values in terms of the negative sign. Even values, positive. Odd values, negative. So j to the fourth power, if we quadruple it now, and we multiply 4 of the square root of minus 1s together, 2 of the terms we've already defined here and seen become a minus 1, and so we end up with a value of 1 positive. Okay? So we've seen that here and we've seen that there. So the J operator. So as we start looking at examples here, let's take a look at minus 144, the square root of minus 144, where we do just like we did before. We factored out the minus 1, and what we end up with then is 12 times the square root of minus 1, or J12. What if we have two terms that we're adding together? So we're going to go back to that negative 36 and add them together. So as I add them together, you can see we, just like we did before, we end up with a value, and then our value that we're going to end up factoring out through the square root, and our minus 1s. So we end up with j, the square root of 36, j, the square root of 36, which ends up being a summation here. What if we're going to do the product and we have different signs? So in doing the product with different signs here, in the second case, there is no negative 1. So that you can see immediately that's going to become 6. The first term is going to be our J6, just like we've seen before. What if we have a product where they're both negative numbers? So we treat them the same, 36 minus 1, 36 minus 1, take the square root of each. We end up now with our first incidence of a j squared times 36. Okay, and multiplying the square root of 36 and the third square root of 36 together, we end up with 36. So, and since j squared gives us a negative value, then we end up with minus 36. Okay, what about a product with a j squared and a j to the fifth? J squared 6 times 6 is equal to just minus 1, negative 6. And if I bring in the second product, the second term, j to the fifth, then that ends up being that negative 6 times j to the fifth. That needs to be corrected. That should be j to the fifth, equals minus j 30. And then minus 36, the square root of, divided by 3. This reduces down to j times 6 equals j2. Okay, that's not an exponent, j2. Okay, this one is an exponent. That one is not. Okay, another one here where we have a quotient, j squared 36 divided by j9. You can see we can factor the j's out just like we've done before. You can see what's going to happen is that this term is going to reduce to just j. 6 into 36 is 4, and we're left with j4. On this one, j24, j squared 6 in the denominator. Again, you can break it up, you don't really need to. what's going to end up happening here is that j is going to stay. So we have j24, and j squared becomes a minus times 6 gives us minus 6, and we can divide that in to end up with a minus j4. Okay, so I think we'll stop here. When we come back, we'll talk about the complex numbers and doing more examples like we've seen, but they end up becoming just a little bit more complicated because we add more terms.